Here we go with section 5.4's video. We're going to tie some ideas together from the most recent chapter and the chapter before. Here's how this idea goes. Let's start with the idea that S is some position is some function of time. Okay, we know lots about that, like, for example, that the derivative of that function S with respect to time is velocity. That's a known fact. Also, we know that we can think of the displacement as the definite integral from A to B of velocity. So, for example, we think of the 0 to 3 hours, 70 miles an hour, and that area there is how much we moved over those 3 hours. So if we know that the integral is a representation of displacement, and we also know that displacement can be simply the position at time B subtracted by the position at time A, well, why don't we just say that those two things are the same? That the integral from A to B of velocity is the same as the displacement S of B minus S of A. Now, let's just talk a little bit more about what we know. We know that if I take the derivative of S, I get V. V is the derivative of S. But to say this in another way, that means S is an antiderivative of V. So if we know this, let's sort of put this idea together. We know that there's this derivative-antiderivative relationship. And we also know that even though I used t in this particular situation, there's no reason why instead of using t, x. In fact, we have a special name for the variables that are in these integration expressions. We call them dummy variables. So whether it's from a to b of v of t dt or a to b of v of x dx, it's all the same. Well, for that matter, I don't even need to use v. What if I use f? And then I said, well, what I have is a relationship between this variable, sorry, this function f and this one, big F, which is a derivative relationship if I go this way, but it's an antiderivative relationship if I go the other way. Okay, if that is the case, then we can summarize this whole big thing into something called the fundamental theorem of calculus part 2. It says, if f is a continuous function on the closed interval from a to b, and if f is any antiderivative of f on that closed interval, then the integral from a to b of f of x dx is equal to this capital F, the antiderivative of f at b minus capital F of a. Now, things that aren't being said here. This doesn't change our definition of a definite integral. The definite integral is still defined by that idea of a Riemann sum, the sum of an infinite number of rectangles filling up a space. What this does say is that if a function that you're looking at has an antiderivative, then we may use that antiderivative in order to find the value of the definite integral. For example, let's evaluate this expression of x cubed plus 1 as it varies from x equals -1 to x equals 3. Okay? I'm going to show you also the form in which we use this fundamental theorem of calculus. Let's try that again. Here we go. The integral from -1 to 3 of the function x cubed plus 1 dx can be thought of. We say, well, what's the antiderivative of x cubed? Well, I'm going to make the power 1 bigger and divide by that number, and then I'll just do a quick check. is the derivative of this equal to x cubed? Bring the power down, the 1/4 and the 4 cancel, lower the power by 1. Yep, we got that. What is the antiderivative of 1? It is x. Do a quick check. The derivative of x is 1. Yep, we got it. And then we're going to do this new thing where we're saying, and we're going to evaluate this expression as x goes from -1 to 3. I'm going to do this part of it first. I'm going to take my upper bound and evaluate that function on the upper bound. 1/4 times 3 to the 4th plus 3. And then I'm going to evaluate this expression at the lower bound. 1/4 times -1 to the 4th plus a -1. All right, let's clean that up a little bit. 3 to the 4th is 81 over 4 plus 3. -1 to the 4th is just 1. So this ends up just being 1/4 and minus 1. See if we clean that up a little bit more. 81/4 plus 3 minus, that would be -3/4, I think. Super plus that. That gives me 81/4 plus 3/4. That's 84/4 plus 3. 4 goes into 84 21 times. Looks like the value of that integral is 24. Okay, and that's using the fundamental theorem of calculus, using the antiderivative to find the value of that definite integral. Now, we're going to have to watch out because this question, find the area of the region of the curve that's between 0 and 3. This question, this area, does not equal to the integral from 0 to 3 of 4 minus x squared. Remember, area can never be negative. And this curve, y equal 4 minus x squared, is a parabola. Starts here at 4 and it goes downward. Where does it cross here? It crosses at the square root of 2. So if we go from 0 to 3, some of this curve is below the axis. You want to find the area then? The area is going to be the integral from 0 to root 2 of 4 minus x squared dx. And then if I go from square root of 2 to 3, this integral is going to produce a bunch of negative values. So we'll subtract off those negative values. We've taken into account that when the curve is below the x-axis, the definite integral produces negative values. All right, now let's go ahead and apply fundamental theorem of calculus part 2 to this. Antiderivative of 4 is 4x minus the antiderivative of x squared. Make the power 1 bigger and divide by that power. And let's evaluate this from 0 to the square root of 2. Let's subtract from that this integral, which is going to be 4x minus 1/3 x cubed, as evaluated from root 2 to 3. Evaluating the first thing on the upper bound, that's 4 root 2 minus 1/3 root 2 cubed minus 4 times 0 minus 1/3 0 cubed. That's a big old 0. I'm going to forget about that. Over on this side, I got to evaluate this first at the high end. That'll be 4 times 3 minus 1/3 3 cubed. That's my evaluation of the antiderivative at the high end. And let's subtract from that, evaluating it at the low end. 4 times root 2 minus 1/3 root 2 root 2 cubed. All right, what do we have here? 4 root 2, okay. Root 2 cubed is 2 root 2. So what I have here is minus root 2 over 3 minus, and now I'm over here, 12. We got root or 3 to the third divided by 3. That's going to be minus 9 minus 4 root 2. I'm sorry, this is all in parentheses. Gotta watch the parentheses. 4 root 2 minus 2 root 2, 2 root 2 over 3. Oh, there's a lot going on there. Let's take care of some distributions. I'm going to distribute this negative sign through these terms. And then I'm going to distribute this negative sign through these terms. Turns into a plus. That turns into a minus. What do we get when we put it all together? I've got 4 root 2 and another 4 root 2. I've got 8 root 2. I've got negative 2 root 2 over 3 plus another negative 2 root 2 over 3. That's negative 4 root 2 over 3. And I've got 12, negative 12 plus 9. I got a negative 3. That looks to me like the common denominator here, 24 root 2 minus 4 root 2 over 3 minus 3, or 20 root 2 over 3 minus 3. And that's a good answer. Right? Okay, great. Now we got one more thing to cover in this situation. You might have been confused that I said that the other one's the fundamental theorem of calculus part 2. You might say, well, where's part 1? Well, we're going to do part 1 right now. Let's take a look again at some pretty big ideas. Let's say I have this perhaps weird thing where g of x is equal to the integral from a to x of f of t dt. So the thing on the right-hand side is a function of x. You give me different values of x, I get integrals that go from a to whatever that value you give me. So the value of that integral varies with x. All right? So it's a function of x. So I should be able to take the derivative of that function of x. So let's try that. Let's say I've got these two things are equal to each other, and I want to find out what g prime is. Take the derivative of both sides. Left-hand side, easy. It's g prime. Using fundamental theorem of calculus, part 2, we could say that this f, I have to take the antiderivative. We'll use the notation that big F is an antiderivative of little f. And so I take the antiderivative of it and I evaluate it on those two lower bound and upper bound. But now I'm going to take the derivative of that. And when I take the derivative of big F, I get big F prime at x. When I take the derivative of big F of a, I get 0 because that is a constant. And the derivative of any constant is 0. Oh, wait, but we define big F as being, we define big F prime as being F. That's the nature of big F being the antiderivative of F. So therefore, I started with this expression here, and when I took the derivative, I simply just got the value of that function inside the integrand evaluated at x. Let's tie it all together. Fundamental theorem of calculus part 1 is that if I have some function given in the form of integral from a to x of f of t dt, all right, then the derivative of that expression with respect to x is simply just f of x. So how easy does this make our life in some circumstances? Well, the derivative of this integral function, it's got the right form. It's a function here, and it's got to the upper bound is x, and that's only x in there. This is simply going to be the cosine of x. Or if I look at this one, same idea. This answer is going to be 1 over 1 plus x squared. Now, is that what all of the problems are going to look like? No, not so fast. What if we have some variation? Like, what if the x is down in the bottom? How can we handle that? Well, for that situation, we simply say, you know what? I can reverse the order of the limits of integration, and I simply just have to put a negative sign out in front. And then we also know that this is like a derivative of something with a constant out in front. There's no reason why I can't just pull that negative all the way out. And if we do that, then this becomes a problem in which I can quite easily just use the fundamental theorem of calculus part 1, and the answer is the sine of x squared. Done. Now, the last variation. What if the limits of integration isn't x, but some function of x? Now, this requires a little thought. Let's walk this through. So I want you to imagine generically that the upper bound of integration is now a function of x. So before we take the derivative of this, we are going to take the antiderivative of little f, we get big F. We're going to evaluate big F at the upper bound and at the lower bound, and then we're going to take the derivative of this whole expression. Well, the derivative of big F of A is just 0 because big F of A is a constant. The derivative of this requires that we use the chain rule. We take the derivative of the outside function, big F, we get big F prime, leave the inside the same. Oh, we have a little error here. And we take the derivative of the inside. So we get G prime there. Oh, wait, but what is big F prime? That's just F. So we get F of G of X times G prime of X as our final answer. Let's see that in action. The derivative of this is going to be the function cosine. Replace t with with that upper bound of x squared. Follow it up with the derivative of that upper bound, 2x. Right? Oh, wait. What if both the top and the bottom have functions of x? All right. Let's think of this one this way. I'm going to take the derivative of 2x to some constant a of 1 over 2 plus e to the t dt. And then I'm going to add to it the integral from a to x squared of the same. As we saw earlier, the first one can be thought of as flipping the limits of integration and putting a negative sign out in front. Well, the second one can proceed just like we talked about in the previous discussion. All right, so what's the derivative of this? It's negative. Every place we see t, we'll replace it with 2x. Don't forget, we're going to multiply that by the derivative of 2x, which is 2, plus 1 over 2 plus e to the x squared, and then follow that with the derivative of x squared, which is 2x. So there's our answer. All right. Last thing that we want to talk about having to do with the fundamental theorems of calculus. And that is, we know that FDC part 2 says this. But if we play around with this a little bit, we get this really, really nice and useful expression. Okay, we start here. Known fact. Is there any reason why I can't add big F of A to both sides? None whatsoever. So if I do that, I get F of B is equal to big F of A plus that integral from A to B. Is there any reason why I need to use the dummy variable X? No. Let's go ahead. Let's change the dummy variable to T. Still no problem. So there's no reason why I can't replace X with T's. There's also no reason why I have to use A's and B's. Maybe I keep the A's the same, but maybe I change this B into an X. No problem there. Lastly, the relationship between F and little f is that big F prime is equal to little f. If I took the derivative of this, I get that. So as long as I have that relationship, I'm good. The derivative of little f is little f prime. Look how powerful that is. It says, let's say I have some function and I know its value someplace. I know what f of a is. And I know how that function changes. Maybe with respect to time, maybe with respect to x, but I know how it changes. If you tell me where I start and you tell me how I change, I can tell you where you end up. I say you start at f of a, and this integral from a to x of f prime of t dt lets you know where the function ends up. Very powerful. Very powerful. All right. It also means that if you tell me those two things, I can find an expression that will represent the equation for that function. So for example, f of 3 is equal to 5. That's a statement of where I started. dy dx is equal to tangent. Great, that's how I change. So can you tell me for any location f of x where I end up? Sure, f of x is equal to f of 3 plus the integral. Remember, there's a 3 here, so that 3 is going to go there. 3 to x of tangent of t dt, or 5 plus the integral from 3 to x of tangent t dt. Now, does this function really have the attributes that I want it to have? For example, does f of 3 equal to 5? Well, I don't know. It's equal to f of 3 is equal to 5 plus the integral from 3 to 3 of tangent t dt. Whoa, wait, this is equal to 0. Yep, f of 3 is equal to 5. Is it true that f prime of x is equal to tan x? I don't know. Let me take the derivative of 3 plus the integral from 3 to x, to t, of x of tangent t dt. Now, the fundamental theorem of calculus part 1 says, says derivative of 3 is 0, and the derivative of that is tangent x, just like I needed it to be. I can create any expression as long as I know where it starts and how it changes. Now you're like, but this is awfully awkward. Shouldn't I find the antiderivative of it? Maybe. If you know the antiderivative, do you know what the antiderivative of tangent t is off the top of your head? Not yet. We'll get there. That concludes today's lecture.